This video covers the basics of quantum mechanics. Let's start with the macroscopic problem of describing the relationship between pressure, temperature, and volume for a certain quantity of an ideal gas. An ideal gas is a theoretical gas composed of many randomly moving point particles that are not subject to interparticle interactions. It is an idealized state. Under some conditions of temperature and pressure, many real gases behave like an ideal gas where the gas molecules play the role of the ideal point particles. Generally, at higher temperatures and at lower pressures, the potential energy due to intermolecular forces becomes less significant compared with the particle's kinetic energy. Also, the size of the molecules becomes less significant compared to the empty space between them, and the gas tends to behave as an ideal gas. Many gases can be treated as ideal gases within reasonable accuracy over a considerable parameter range around standard temperature and pressure. Several scientists contributed to the description of the ideal gas behavior described by the ideal gas equation of state. Robert Boyle was born on January 25, 1627 and died on December 31, 1691. He was an Anglo-Irish natural philosopher, chemist, physicist, alchemist and inventor. Boyle is largely regarded today as the first modern chemist. Edmund Marriott was born on 1620 and died on May 12, 1684. He was a French physicist and priest. He is particularly well known for formulating Boyle's law independently of Robert Boyle. Jacques-Alexandre César Charles was born on November 12, 1746 and died on April 7, 1823. He was a French inventor, scientist, mathematician, and balloonist. Joseph-Louis Gay-Lussac was born on December 6, 1778 and died on May 9, 1850. He was a French chemist and physicist. He is known mostly for his discovery that water is made of 2 parts hydrogen and 1 part oxygen by volume. Benoit Paul-Émile Clapeyron was born on January 26, 1799 and died on January 28, 1864. He was a French engineer and physicist, one of the founders of thermodynamics. The ideal gas law equation of state describes the relationship between the pressure P, the volume V, and the temperature T, for a certain number n of moles of an ideal gas. R is called the ideal gas constant. It was first stated by Clapeyron in 1834 as a combination of the empirical Boyle's law, Charles's law, Avogadro's law, and Gay-Lussac's law. The number of moles is the total number of molecules n, divided by Avogadro constant Na. The Avogadro number is the number of molecules per mole and is equal to. If we divide the constant R by the Avogadro number, we obtain another constant named Boltzmann constant. We will see later why it is called Boltzmann constant. For now it is sufficient to interpret it as the gas ideal constant on a per molecule basis instead of a per mole basis. Then the ideal equation of state can be written on a molecule basis as Daniel Bernoulli was born on February 8, 1700 and died on March 27, 1782. He was a Swiss mathematician and physicist. He made important contributions to fluid mechanics. In 1738, Bernoulli published his book titled Hydrodynamics, which laid the basis for the kinetic theory of gases. In this work, Bernoulli proposed that gases consist of great numbers of molecules moving in all directions, that their impact on a surface causes the pressure of the gas, and that their average kinetic energy determines the temperature of the gas. Imagine a large group of small particles moving in space. The average velocity of the particles in any direction is identical. Let's imagine a solid sphere surrounding a group of n perfectly spherical gas molecules. The sphere radius is r. Since the average velocity of the particles in any direction is identical, we will focus on the average radial velocity of the particles v. The average time interval between 2 consecutive bounces of a particle with the container wall is. Imagine the bounce is a completely elastic collision. Then, the average momentum change for the particle due to the bounce with the wall is. This momentum change is related to the impulse exerted by the wall force on the particle. Combining those equations yields. The area where this force is acting on is. The sphere volume is. The relationship between the wall area, the sphere volume and the sphere radius is. The pressure exerted by n particles on the container wall is. Or which simplifies to. This can be written as, but kinetic energy is, and therefore, we have. This is a very important equation. It relates two macroscopic properties, namely the pressure P and the volume V with the average kinetic energy K, which is a microscopic property. The ideal gas equation of state also relates some of those variables. Comparing both equations, we can write, which states that the molecule's average kinetic energy is related to the macroscopic gas temperature. This provides another interpretation for the Boltzmann constant. With this result, a new statistical mechanics science was born linking microscopic statistical variables with macroscopic measurable quantities. Viscosity, diffusion coefficient, thermal conductivity, etc. were all later explained by this new scientific branch known as kinetic theory of gases. James Clerk Maxwell was born on June 13, 1831 and died on November 5, 1879. He was a Scottish physicist and mathematician who was responsible for the classical theory of electromagnetic radiation, which was the first theory to describe electricity, magnetism and light as different manifestations of the same phenomenon. Maxwell was also key in the creation of statistical mechanics. Ludwig Edward Boltzmann was born on February 20, 1844 and died on September 5, 1906. He was an Austrian physicist and philosopher. His greatest achievements were the development of statistical mechanics and the statistical explanation of the second law of thermodynamics. In 1859, Maxwell argued that the kinetic heat energy of a gas is equally divided between linear and rotational energy. In 1876, Boltzmann expanded on this principle by showing that the average energy was divided equally among all the independent components of motion in a system. This became known as the equipartition theorem of energy. The total average kinetic energy of the particles is given by, or, and therefore, the average velocity square is given by. But in thermal equilibrium, the average velocities in all directions are the same. Therefore, where kx is the average kinetic energy in x direction. From this we can see, which means that the total kinetic energy is split equally in the kinetic energy in all three directions. The original idea of equipartitioning is that in thermal equilibrium, the total internal energy U is shared equally among its all various forms per degree of freedom. If F is the number of degrees of freedom, then the rate of change of the total internal energy U with temperature is. For diatomic molecules shaped like a rod, we have 3 degrees of freedom for translation, but only 2 degrees of freedom for rotation, since rotation around the molecule axis has a zero moment of inertia, and therefore, for diatomic gases the rate of change of internal energy with temperature is. Gustav Robert Kirchhoff was born on March 12, 1824 and died on October 17, 1887. He was a German physicist, mathematician and chemist who contributed to the fundamental understanding of electrical circuits, spectroscopy and the emission of black-body radiation. In 1859, Kirchhoff was the first to study the problem that now we call black-body radiation. Before Kirchhoff's law was recognized, it had been experimentally established that a good absorber is a good emitter, and a poor absorber is a poor emitter. Naturally, a good reflector must be a poor absorber. This is why, for example, lightweight emergency thermal blankets are based on reflective metallic coatings. They lose little heat by radiation. Kirchhoff's law of thermal radiation states that for any thermally radiating body in thermal equilibrium, the amount of energy absorbed at a certain frequency is equal to the amount of energy emitted at the same frequency. The radiation represents a conversion of a body's internal energy into electromagnetic energy and is therefore called thermal radiation. Blacksmiths have always used light color as an indicator of the temperature of the steel they are working on. This guides them on how to conduct many thermophysical changes such as annealing, hardening, and tempering. With their practice, they become used to relate the steel temperature with the color light it emits. A black body is an idealized physical body that absorbs all incident electromagnetic radiation, regardless of frequency or angle of incidence. The radiation emitted by a black body in thermal equilibrium with its environment is called black body radiation. The name black body is given because it absorbs all colors of light. In contrast, a white body is one with a rough surface that reflects all incident rays completely and uniformly in all directions. A black body at room temperature of 23 degrees Celsius radiates mostly in the infrared spectrum, which cannot be perceived by the human eye, but can be sensed by some reptiles and infrared sensors. As the object increases in temperature to about 500 degrees Celsius, the emission spectrum gets stronger and extends into the human visual range, and the object appears dull red. As its temperature increases further, it emits more and more orange, yellow, green, blue, indigo, violet light and ultimately ultraviolet. The concept of the black body is an idealization, as perfect black bodies do not exist in nature. However, graphite with emissivities greater than 0.95 is a good approximation to a black material. A closed box with walls of graphite at a constant temperature with a small hole on one side produces a good approximation to ideal blackbody radiation emanating from the opening. Any radiation inside the cavity is absorbed by the graphite and re-emitted, therefore the object remains in thermal equilibrium. The only energy leaving the box is a tiny amount through the small hole. The intensity of an electromagnetic radiation is the amount of energy moving onto, through or from a surface per unit time. This is called the radiant flux. It is measured in energy per second or power. Radiance is a directional property, which is described as the radiant flux per unit area of the emitting surface perpendicular to the direction and per solid angle. Spectral radiance in frequency of a surface is defined as the rate of change of radiance with frequency. Spectral radiance in wavelength of a surface is defined as the rate of change of radiance with wavelength. The relationship between frequency and wavelength of a wave is therefore. And we can use this relationship to find the transformation between spectral radiances. In those equations, we still need to change frequency into wavelength and vice versa in the expressions of spectral radiance, otherwise we will be left with both variables instead of just one. A graph of the amount of spectral radiance versus frequency or wavelength for the energy emitted by a blackbody is called the blackbody curve. Different curves are obtained by varying the blackbody cavity temperature. The more common presentation of the blackbody radiation curve is the spectral radiance in wavelength. Michael Faraday was born on September 22, 1791 and died on August 25, 1867. He was an English physicist and chemist who contributed to the study of electromagnetism and electrochemistry. Franz Emil Melde was born on March 11, 1832 and died on March 17, 1901. He was a German physicist and professor, focusing primarily on acoustics. The wave on a fixed end strings is what we called a stationary wave. If the length or tension of the string is correctly adjusted, the sound produced is a musical tone. Vibrating strings are the basis of string instruments such as guitars, cellos, and pianos. A stationary wave is a wave that oscillates in time but whose peak amplitude profile does not move in space. The peak amplitude of the wave oscillations at any point in space is constant with respect to time, and the oscillations at different points throughout the wave are in phase. The locations at which the absolute value of the amplitude is minimum are called nodes, and the locations where the absolute value of the amplitude is maximum are called antinodes. Standing waves were first described scientifically by Faraday in 1831 when observing waves on the surface of a liquid in a vibrating container. Melda coined the term standing wave and demonstrated the phenomenon in his classic experiment with vibrating strings. Standing waves can occur due to several conditions, but we are interested in standing waves created as a result of interference between two waves traveling in opposite directions. Let's look at two-dimensional traveling waves. The red wave traveling to the right is described by the following equation. The blue wave traveling to the left is described by the following equation. The standing wave created by the superposition of those two waves is described by the following equation. After using geometric relationships for the sum of angles we obtain, which can be rewritten as where the amplitude of oscillation A is only a function of the position, and the oscillation with time B is only a function of time. Let's imagine a wave with fixed points at a position x equal to 0 and at another position x equal to L. Standing waves of this type do not transfer energy at the boundaries since the ends are fixed. Those are the waves that occur in string instruments. The standing wave equation is: at position x equal to 0, the wave already has an amplitude of 0. The fixed end condition at a position x of L is written as this last equation yields. But the wave number k is defined as the angle in radians per unitary distance. Combining those two equations yields the wave number. The frequency and wavelength in instruments such as a guitar are not continuous, they are discrete. For each value of n we have different harmonics of the principal harmonic when n is equal to 1. Finally, the standing wave equation with fixed ends can be written as or where A is only a function of x and B is only a function of t. The wave on a string equation is: for a standing wave on a string with length L, we have the following boundary and initial conditions. The general solution is a superposition of the several harmonics, where the index is n corresponds to the several harmonics. The coefficients Bn can be determined from the initial condition as the electromagnetic wave equation is or in Cartesian coordinates. Let's find the equations for standing waves in a cube that don't transfer energy at the boundaries. Let's imagine a cube with one of the vertices at the origin of a three-dimensional Cartesian coordinate system. The sides of the cube are equal to L, and they are aligned with the coordinate axes x, y, and z. The standing wave solution must have a sinusoidal form in x, y, and z coordinates with 0 value when the coordinates are 0 and L. The solution then has the general form. The second derivatives of this function with respect to x, y, z, and t are substituting this into the wave equation yields each combination of nx, ny, and nz that satisfy this equation constitutes a vibration mode. For instance, if instead of finding the vibration modes of standing waves inside a cube we were interested in the standing waves in a square membrane, the equation for the vibrational modes would be each vibrational mode is represented by a pair of the values for nx and ny. An example of the first four vibrational modes in a square membrane are 1, 1, 1, 2, 2, 1, and 2, 2. The solution of standing waves in a two-dimensional membrane is a superposition of all the different individual harmonic solutions in both directions. Returning to the standing waves in a cube equation, we have this equation can be seen as the equation for a sphere in n space where nx, ny, and nz are discrete positive coordinates, and the sphere radius is the relationship between the many harmonics is then. Let's assume that for a value of r we have m possible modes. The combination of nx, ny, and nz for each mode lies on surface of the sphere. However, since we are using only positive values for n, we need to consider only the 1/8 of sphere that lies in the positive octant. And since in any direction the electromagnetic waves may have two polarizations, the area we need to consider is if we increase the radius of the sphere by dr, the change in the number of modes is dm. But we have, and we obtain, or in terms of frequencies, we have. So the number of modes per cavity volume per wavelength and per frequency are We are already familiar with James Clerk Maxwell and Ludwig Edward Boltzmann other contributions. In probabilistic mechanics, Maxwell-Boltzmann distribution describes how material particles can be distributed over various energy states in thermal equilibrium. The distribution was first derived by Maxwell in 1860 on heuristic grounds. Boltzmann in the 1870s laid out a sound mathematical background for its use in many fields. A microstate is a specific arrangement of the constituent parts of a system that produces an externally observable macrostate. A macrostate may have one or several microstates. The number of microstates per macrostate is called multiplicity. Let's look at some examples. Let's determine the macrostates, that is the observable results, and the corresponding microstates for the experiment of flipping two coins on a table. The macrostates are the number of tails t and heads h that are observed. So there are 3 macrostates and 4 microstates, with the macrostate of a head and a tail having multiplicity of 2. Imagine now the throwing of 2 dice on a table. The macrostates could be the sum of the faces standing up on the table. The microstates are the many arrangements that produce that result. There are 11 macrostates and 36 microstates. Another example is how many ways we can arrange 4 different particles into 2 boxes. There are 16 possible unique arrangements. The overall number of particles in one bin defines the macrostate since the remaining particles must be in the other box. Therefore, there are 3 macrostates and 16 microstates. Let's say now that the order of the boxes is important. In this case there are 5 macrostates with the same 16 microstates. For a final example, assume that we have a set of small particles that distinguishable by only one characteristic while all other properties are identical. For instance, they could have different discrete values of kinetic energy from 0 to 6. A macrostate in this case is the sum of the number of particles in a certain group times the property or energy characteristic of the group, or the total kinetic energy for the set of particles. For example, imagine 4 particles to be distributed among groups with discrete integer kinetic energy values from 0 to 6. Imagine now a macrostate with total kinetic energy of 6. The 9 microstates for this particular macrostate are: suppose we have a system composed of a large number of small identical particles. For instance, the particles are spherical molecules of a monoatomic gas. The particles can be categorized into different groups according to the value epsilon I of a distinguishable property. Let the number of particles on any of those groups be Ni. The total number of arrangements that n particles can be assigned into I groups is as follows. For the first group we can select n1 out of n particles and place them in group epsilon I1. For group 2 we can only select n2 out of n-n1 particles to place them on group epsilon I2. Therefore, the total number W of ways of distributing those particles is, which results in, this is the number of total microstates. It can be written in a more concise way as, we can write this as, an equilibrium state will be achieved when W is maximized given the constraints that the total number of particles is fixed and the total property for the particle set is also fixed. Maximizing the objective function W is the same as maximizing the natural log of W. Assume the particle's distinguishable property is the particle's kinetic energy and the macrostate is a no total kinetic energy. The problem of finding the equilibrium state is written as, Stirling's approximation for the factorial function states that using Stirling's approximation we obtain. So the maximization problem subjected to the constraints of the known total number of particles and total energy of the system becomes Lagrange multipliers technique transforms this problem into the problem of maximizing the function, where function f is the original objective function plus the two constraints equations multiplied by factors alpha and beta known as Lagrangian multipliers. So the problem becomes, the maximum occurs when the first equation yields. Since the terms in the summation are independent, the summation can only be 0 when each term is 0. Or the second equation yields. Or so the first Lagrange multiplier satisfies the following equation. The number of particle per energy level is, or and finally, the third equation is, or using the first Lagrange multiplier relationship we have, or assuming that the particle's property is a function of a continuous variable x we have and we can write let's investigate the kinetic energy distribution for monoatomic gases. The kinetic energy of a molecule in one specific direction x is, for a continuous distribution we have, and then the distribution of particle becomes, and our average energy per particle becomes, from the gas kinetic theory, and using the equipartition theorem we have. So, and the distribution of particles can be written as Wilhelm Karl Werner Otto Fritz Franz Wien was born on January 13, 1864 and died on August 30, 1928. He was a German physicist. He formulated two expressions related to the blackbody radiation problem. Wien received the Nobel Prize in Physics in 1911 for his work on heat radiation. Louis Karl Heinrich Friedrich Paschen was born on January 22, 1865, and died on February 25, 1947. He was a German physicist, known for his work on electrical discharges. He is also known for the Paschen series, a series of hydrogen spectral lines in the infrared region that he first observed in 1908. In 1896, Wilhelm Wien came up with a law, based on a thermodynamical argument, which almost solved the blackbody problem. Wien's distribution law for spectral radiance in frequency and in wavelength are, where A and B are empirical constants to be determined from experimental data. In his original paper, Wien mentioned that Friedrich Paschen independently obtained the same expression and was intended to determine the value of the constant A from experimental data. Wien also presented a correlation for the value of the frequency or wavelength where the blackbody radiance will peak. His correlation, known as Wien's displacement law, is if we take Wien's radiance equation in wavelength and take the derivative with respect to the wavelength we get, the peak wavelength can be determined from. Comparing this result with Wien's displacement law, we can write: Wien determined the value of C' and B from experimental data as. Wien's equation does a really good job in approximating the blackbody radiation if we use a constant A of. For many, including Planck, the problem of blackbody radiation had been solved by Wien and Paschen, but there were problems ahead. John William Strutt, 3rd Baron Rayleigh, was born on November 1842 and died on June 30, 1919. He was an English physicist and mathematician. He spent all of his academic career at the University of Cambridge and received the Nobel Prize in Physics in 1904 for the discovery of argon. He served as President of the Royal Society from 1905 to 1908 and as Chancellor of the University of Cambridge from 1908 to 1919. James Hopwood Jeans was born on September 11, 1877 and died on September 16, 1946. He was an English physicist, astronomer and mathematician. The other important work on blackbody radiation was conducted by Rayleigh and is known as the Rayleigh-Jeans law. Rayleigh and Jeans assumed that the waves inside the blackbody cavity are standing waves that can be decomposed into a set of standing waves vibrating in the three spatial directions. We have already seen that the number of modes per cavity volume per wavelength and per frequency are. If we consider that each mode is an harmonic oscillator with a potential and kinetic energy, and using the equipartition we have the energy per mode as and the energy concentration per volume per frequency and per wavelength are. The spectral radiance is defined as and therefore or in terms of frequency. The expressions for the spectral radiance in frequency and wavelength are Wien's equation has the correct shape for the blackbody radiation and agrees with experimental data on the short wavelength region. Rayleigh-Jeans law agrees with experimental data at long wavelengths, but at short wavelengths it deviated significantly from the experimental data, predicting infinite spectral radiance as the wavelengths approach the ultraviolet range. This was known as the ultraviolet catastrophe. Max Carl Ernst Ludwig Planck was born on April 23, 1858 and died on October 4, 1947. He was a German theoretical physicist. He made many substantial contributions to theoretical physics, but his fame as a physicist rests primarily on his role as the originator of quantum theory, which revolutionized understanding of atomic and subatomic processes and won him the Nobel Prize in Physics in 1918. Gustav Kirchhoff was Max Planck's teacher and proposed the existence of a universal law for blackbody radiation, and this was called Kirchhoff's challenge. Planck believed that Wilhelm Wien had discovered this law. Experiments appeared to support Wien's law, especially at short wavelengths. Rayleigh published his first derivation of the blackbody radiance in June 1900, and it correctly predicted the behavior at longer wavelengths. By September 1900, experimentalists had proven beyond a doubt that the Wien law failed at the longer wavelengths. Planck submitted a formula combining both Rayleigh's law and Wien's law, which would be weighted to one or the other law depending on wavelength to match the experimental data. Planck wanted an equation that reproduced Wien's equation for short wavelengths and Rayleigh's equation for long wavelengths. Planck proposed the following equation based on two auxiliary variables g and h. At longer wavelengths, this expression should approach Rayleigh's equation. At shorter wavelengths, this expression should approach Wien's equation. The limits of the expression proposed by Planck are the parameter g and h are determined as follows. By inspection, we conclude from the second equation. And a is determined as. From the first equation, we obtain g as now Planck's proposed equation becomes, which now is only a function of a parameter b. Planck decided to introduce a new constant. He called this new constant h, probably in reference to Hilfsgröße, which means auxiliary variable in German. With this, b becomes. From the experimental data, Planck determined the value of h to be and replacing this in his equation yields Planck's final equation, which agree with experimental data across all values of wavelength. Although this equation worked, Planck himself said,
"Unless I can explain the formula derived from a lucky intuition into one with a true meaning in physics, it does not have true significance."
The energy associated with the electromagnetic waves is stored in the oscillating electric and magnetic fields. Only a certain discrete number of modes are allowed for standing electromagnetic waves. This means that for a certain frequency, the energy of a particular mode cannot have arbitrary energy values. Planck proposed that the energy values are discrete and must be the number of modes times the energy per mode at that frequency. We call this the energy of a photon. For a mode that contains mi photons, the mode energy is, where mi is the number of photons on this mode. The average energy of the photons with this frequency is then let's call. Then we have expanding the summations we obtain. The numerator and denominator in the fractions can be recognized as series expansions of. Therefore we have replacing x we obtain, or in terms of wavelength. Since each photon has an energy equal to, we conclude that the average number of photons at a certain frequency or wavelength is. We can now write, or in terms of frequency. For standing waves in a cavity we have. And therefore, the radiance is defined as, and Planck's equation for the blackbody radiance are finally written as the photoelectric effect is the emission of electrons from a material caused by electromagnetic radiation. Electrons emitted in this manner are called photoelectrons. Classical electromagnetism predicted that continuous light waves transfer energy to electrons, which would then be emitted when they accumulate enough energy. An alteration in the intensity of light would theoretically change the kinetic energy of the emitted electrons, with sufficiently dim light resulting in a delayed emission. The experimental results instead show that electrons are dislodged only when the light exceeds a certain threshold frequency regardless of the light's intensity or duration of exposure. Because a low-frequency beam at a high intensity does not build up the energy required to produce photoelectrons, as would be the case if light's energy accumulated over time from a continuous wave. This was a problem in the beginning of the 20th century waiting for an explanation. We are already familiar with Albert Einstein. Gilbert Newton Lewis was born on October 25, 1875 and died on March 23, 1946. He was an American physical chemist and a dean of the College of Chemistry at University of California, Berkeley. This picture shows the experiment used to demonstrate the photoelectric effect. Filtered, monochromatic light of a certain wavelength strikes the emitting electrode inside a vacuum tube. The collector electrode is at a certain voltage potential. The photocurrent generated is plotted against the voltage potential difference between the electrodes. For the positive potential difference, the current steadily grows until it reaches a plateau. For the negative potential difference, the value of the photocurrent decreases and becomes zero at a certain voltage V sub S called the stopping potential. For any intensity of incident radiation, whether the intensity is high or low, the value of the stopping potential remains constant. Einstein reasoned in 1905 that if Planck's hypothesis about energy quanta was correct for describing the energy exchange between electromagnetic radiation and cavity walls, it should also work to describe energy absorption from electromagnetic radiation by the surface of a photoelectrode. He postulated that an electromagnetic wave carries its energy in discrete quantized energy packets. According to Einstein, when an energy packet arrives at the metal surface, all of its energy is transferred to only one electron on the metal surface. According to Planck, this energy is an energy balance on the electron charge Q sub E moving between the electrodes yields a relationship between the maximum kinetic energy acquired by the electron and the stopping potential V sub S. For the electron to be removed from the metal surface, it needs to gain a certain energy phi to overcome its binding energy. Therefore, an energy balance for the process yields, which can be written as Einstein plot the stop voltage as a function of the frequency. The resulting straight line has a slope that is equal to the Planck's constant h divided by the electron charge. With this, he was able to calculate a more precise value for Planck's constant and explain the photoelectric effect. In the photoemission process, when an electron within some material absorbs the energy of a photon and acquires more energy than its binding energy, it is likely to be ejected. If the photon energy is too low, the electron is unable to escape the material. Since an increase in the intensity of low-frequency light will only increase the number of low-energy photons, this change in intensity will not create any single photon with enough energy to dislodge an electron. Moreover, the energy of the emitted electrons will not depend on the intensity of the incoming light of a given frequency, but only on the energy of the individual photons. Lewis in 1926 coined the term photon for the smallest unit of radiant energy proposed by Einstein. According to Einstein, the photons of a light beam have a characteristic energy, called photon energy, which is proportional to the frequency of the light. Photon has been there all around us for everyone to see, but it took Planck, Einstein, and Gilbert to properly characterize it. Niels Henrik David Bohr was born on October 7, 1885 and died on November 18, 1962. He was a Danish physicist who made foundational contributions to understanding atomic structure and quantum theory, for which he received the Nobel Prize in Physics in 1922. Bohr was familiar with Maxwell's theory of classical electromagnetism and knew that in a classical theory, the orbiting electron as a particle should radiate energy away and eventually collapse into the nucleus. He circumvented this problem by following Planck's idea underlying blackbody radiation and postulating that the orbital angular momentum of the electron could only take on specific values. He started with Rutherford's model. Then he postulated that the angular momentum of the electrons were quantized, which yields discrete values for the orbit radius. The Bohr radius, denoted as a sub-zero, is a physical constant, equal to the distance between the nucleus and the electron in a hydrogen atom in its ground state. For z of 1 and n of 1, the Bohr radius is. The value for the Bohr radius is. The total energy is. Or substituting the value for r, we obtain the equation for the quantized energy levels. This model now can even explain the emission and absorption phenomena. Imagine an atom loses energy by emitting a photon going from initial to a final state. The frequency emitted is then. Using Bohr's model equation for energy, we obtain. Or in terms of wavelength, which provided a theoretical basis for Rydberg's empirical equation for the hydrogen atom spectrum. Bohr theory modified the atomic structure model by explaining that electrons move in fixed orbitals, shells, and not anywhere in between, and he also explained that each orbit, shell, has a fixed energy. Rutherford explained the nucleus of an atom, and Bohr modified that model into electrons and their energy levels. Louis Victor Pierre Raymond, 7th Duc de Broglie, was born on August 15, 1892 and died on March 19, 1987. He was a French physicist and aristocrat who made groundbreaking contributions to quantum theory. In his 1924 PhD thesis, he postulated the wave nature of electrons and suggested that all matter has wave properties. De Broglie won the Nobel Prize in Physics in 1929 after the wave-like behavior of matter was first experimentally demonstrated in 1927 using electrons, and it has also been confirmed for other elementary particles, neutral atoms and molecules. De Broglie became the first high-level scientist to call for establishment of a multinational laboratory, a proposal that led to the establishment of the European Organization for Nuclear Research, CERN. The results we have examined so far indicate a relationship between matter and wave characteristics of particles. Einstein and Gilbert provided a way to investigate the photon as a particle with matter and wave properties. The de Broglie wavelength is the wavelength, lambda, associated with a particle with momentum p through the Planck constant, h. De Broglie energy refers to the energy associated with a particle based on its wave-like properties. The energy of a particle is related to its associated wave frequency or wavelength through the equation. So the matter-wave properties only depend on the frequency of the wave. The relationship between the de Broglie energy and momentum is, and this is consistent with Einstein's special relativity energy-momentum relationship for matter, which is. So de Broglie relationships show that even massless particles can possess momentum and energy. In particular, for a photon we have. Thus, one can use light to impart momentum to something. This is how a solar sail, a proposed propulsion mechanism for space travel, operates. The space probe Icarus, launched in 2010, was the first practical solar sail vehicle. As of 2015, it was still under thrust, proving the practicality of a solar sail for long-duration missions. Its mission was officially terminated by the Japan Aerospace Exploration Agency on May 15, 2025, and has been out of contact with ground control since then. Clinton Joseph Davison was born on October 22, 1881 and died on February 1, 1958. He was an American physicist. Lester Halbert Germer was born on October 10, 1896 and died on October 3, 1971. He was an American physicist. George Paget Thomson was born on May 3, 1892 and died on September 10, 1975. He was a British physicist and son of Joseph John Thomson. In 1927, Davison and Germer shot electron particles onto a nickel crystal. At that time, they were investigating the angle distribution of the elastically scattered electrons from the face of a polycrystalline nickel composed of many randomly oriented crystals. During the experiment, air entered in the vacuum chamber where the nickel was, producing an oxide layer on its surface. Davison and Clinton reduced the nickel by heating it at high temperature. They did not realize that the thermal treatment changed the polycrystalline nickel to a nearly monocrystalline nickel composed of many oriented crystals. When they repeated the experiment, the distribution in angle of the scattered electrons manifested sharp peaks at certain angles similar to the interference patterns of X-ray diffraction. This result proved the duality character of matter and waves. In the same year, Thomson fired electrons towards thin metal foil, providing him with the same results as Davison and Germer. It was an experimental milestone in the creation of quantum mechanics. Davison and Thomson shared the 1937 Nobel Prize in Physics. J.J. Thomson showed that the electron is a particle 31 years before. His son showed that it is also a wave. Louis de Broglie made a significant contribution to quantum mechanics by proposing the concept of matter waves, which states that all matter, including particles like electrons, can exhibit wave-like behavior, essentially introducing the idea of wave-particle duality as a fundamental principle within quantum mechanics. It was just a matter of time for scientists to propose a wave equation to describe the behavior of matter. This will be covered in the Schrödinger's equation video.